Markov chains. So Markov chains are described like this. So you have different states. So here we have state 0 and state 1. And then you have changes between the states. So the amount of things that change from state 0 to state 1 is all of it, so 1. The amount of state 1 that changed to 0 is half, and the amount that changed from 1 to 1 is half. The amount leaving always has to equal 1. So if you look here, there's only one arrow coming out of 0, but it's 1. If you were to add up the arrows coming out of 1, it's half, and plus half, that's 1. Now, let's talk about the pi thing. So pi I is the proportion of things at state I after a long while, right? So let's basically, because it's proportion again, then the sum of all those pi's has to equal to I. And the way we do this is by basically cutting up the links between states and writing equations for them. So in this scenario, we can see that A, is the amount of X, the amount of things leaving X, right? Like that proportion. The proportion of Y is B. So we can write this relationship. Now, let's look at the first example, which is what we showed up here. It's very simple, so it should be pretty straightforward to follow. If we were to cut right here, right? If we were to cut, all of 0 goes to 1, so we could just write pi 0, and half of 1 goes to 0. So we have half of pi I and 1 pi 0. From there, we can go back to this equation. The sum of all the pi's has to equal 1, and we have 1 is equal to this. We write out pi 0 plus pi 1, but we know what pi 0 is, so we can just plug that in, and now we only have pi 1. We can now solve for it, and we get 2/3. Plugging it back into this equation now, right, we get pi 0 is equal to 1/3, which makes sense. 2/3 plus 1/3 is 1. So we have our pi vector, which is 1/3, 2/3. So that would be enough to answer this question. Now, this one is a little harder. So Blockbuster, just the blue and yellow thing, I know you know, allows you to rent movies from 3 locations, A, B, and C. People who pick it up at A return 1/3 of their movies to A, 1/3 of those people return them to B, and 1/3 of those people return it to C. Now, people who pick up at B return 1/4 of their movies to A, or 1/4 of the people who pick up movies at B return it to A, half return it to B, and 1/4 return it to C. And those who pick it up at C, all of those people return it to A. So we can actually write a Markov chain, right, where I labeled it here, where there's the red ones are the red arrows leaving A. Again, they all add up to 1. Green are the arrows leaving B, which describe this sentence. And then blue, there's only 1, which is all of C. Return them to A. Now we can make the cuts, right? So let's make the cut between A and B. Pretty straightforward. A third, a fourth, right? For B and C, we actually have a 0 in here, so we're going to ignore that. If there's only arrows going towards one or just leaving it and not going and entering into both, you cannot write a relationship for it. So you just, nothing there. Now between C and A, there's a 1 and a third, so 1 and a third. Now, in this scenario, in the first scenario, we didn't need to do this, but we need to do this in most scenarios, which is writing it in terms of a specific pi. So let's write it in terms of pi A. So if we rearrange this, pi A is equal to, well, not this one, but pi A is obviously equal to pi A. That's just obvious. Now, pi B is equal to 4/3 pi A, right, which is rearranging this. And pi C is equal to 1/3 pi A, which is just not even touching that one. Now, we go back to this equation, the sum of all of them. We can replace pi B and pi C with these and pull out the pi A, which now, again, we only have one variable. We can solve for it, and we get this. Now, taking these equations and just plugging in that 3/8 gives us these numbers, which means we now know the pi vector for this. So a problem that looked pretty confusing at first is actually pretty straightforward and easy to do with this Markov chain kind of technique. So good luck, you're going to do great.